I should say that in my mind, the conference title has changed to similarities between algebra and topology. I don't think I'll get to any duality at all, and maybe I'll get to stratification. So today I want to talk around completions. I've been talking enough about local cohomology. Okay, let me start by, as always in my lectures, it will be, R will be a commutative Noetherian ring. Please let me know if the writing gets too small. It will get small. Too small is the problem. And DFR is going to be the derived category as usual, the full derived category. Now, let me say at the outset that most of what I'm going to say in this lecture, it applies basically to very general triangulated categories, maybe with a tensor product, or in particular to the stable homotopy category or the stable category of a finite group and so on. So I'm going to try and talk about concepts in a way that are easily transported. And in fact, that's one of the points about this exercise, that the derived category of a commutative ring is in many cases a reasonably simple model to test or understand many ideas. Okay, so that's okay. So now I'm going to look at the spectrum of the ring. It's the collection of prime ideals, and I'll fix a subset which is specialization closed. This came up already in Henning's lecture yesterday, I believe. So what this means is that, a quick reminder, if you have two primes P and Q, if P is in V and P contained in Q, if P is in the subset, then so is V. And this is equivalent to saying that V contains the closure of its points in the Zariski topology. Okay, but you really don't need to bring in topology. It's really a set theory. It's just this. Okay. Of course, every closed set is specialization closed, but a specialization closed is just the union of closed sets. So in fact, you can write V as a union of those sets where the PI are minimal. With respect to inclusion in V. So you can, these are the components of V. But the only thing is the union is not necessarily finite. So you can have infinitely many components. Okay. So then recall that we discussed, given a module M, I introduced the V torsion part of M. And the V torsion part of M is by definition the kernel of the map is. So it's the submodule. So the submodule consists of elements supported on V. So this is our V torsion submodule M. All right, and then we looked at the derived functor, which is the local cohomology functor. So for M in the derived category, so you can look at, apply this to the injective resolution. So this is going to be injective resolution of M. So, and then this of course sits inside this. So this is the local cohomology supported on V, or the local cohomology functor supported on V. Right? And so we have this map here to here. And we discussed last time, or the last time I spoke, that this is cellular approximation with respect to the V torsion objects. Okay, and moving on. So let me set MVDR to be the collection of V torsion complexes. So you're looking at complexes which are entirely supported on V. Okay? So this is the V torsion part of the derived category. And it's not so difficult to check that this is a localizing subcategory of DR. That's a localizing subcategory. And in fact, so we have a localizing subcategory, and this sits inside DR. So this is a localizing subcategory, and the local cohomology functor is a right adjoint to that inclusion. Okay. Now, this has even better properties too, so you can even identify the compact objects in this category. Let me describe the compact objects. In the gamma, this category, yeah. Okay, to that end, okay, so here's, in fact, I can just say, let me just say what it is, and I'll say it more. So if you look at this, this is a triangulated category in its own right. And the compact objects in the category are nothing but the compact objects in the big category, which are torsion, V torsion. So remember, the compact objects in the derived category are just the perfect complexes. So what this is saying is that the compact objects in this subcategory are precisely the compact objects here that are supported on V. One can do better than this. One can even identify generators for this. So let's take the decomposition that I wrote down earlier, and let K be the causal complex on a generating set for PI. Causal complex on PI, by which I mean pick any generating set for PI, construct the causal complex. Okay. Of course, this is not so, I mean, it's not well defined as a complex. It depends on your choice, but it's an exercise to see that different choices give you the same, they build the same objects. So yeah, they're all defining the same thick subcategory. Okay, so then the claim is that then the compact objects here are all generated by these causal complexes for various I. So every compact object is built out of this. And moreover, the V torsion part itself is compact. So this is compactly generated, so you can build it out of these causal complexes. So this is, maybe I should start marking. This requires a proof, of course, but let me leave it at that for the moment. It's easy to see that these things are supported on V because I've just taken causal complexes on this. But it requires a little bit of proof to show that these actually compactly generate the V torsion subcategory. So this fact has a lot of consequences, and I want to record some of them. So the first thing is the following. So let's look at, for each M, you can, so if you look at M in DR, you can look at this local cohomology functor, and you can complete it to a triangle. This is, and let me write this, just to remind you that I'm completing it to a triangle, write it like this. So this one here, I think of as localization away from V. So the topologist might prefer to think of this as nullification with respect to the V torsion objects. You can also realize this as an example of homology localization that Constanza was talking about in her lectures. Okay, and okay, by the way, the reason I'm thinking of this as a localization is because of this example. So if you fix a prime P and you look at this specialization closed set. So I want to look at the spectrum of the ring, but throw away the primes that are contained in P, namely the spectrum of R localized at P. So you can check that this is specialization closed, and then it's not hard to see. I think actually I should leave it as an exercise. It's not hard to see that localization with respect to this specialization closed set is nothing but localization at M of M at P. So this process it's for this reason that I think of this as localization. All right. Okay. So back to this. So the fact that this is compactly generated, that it is compactly generated by objects that are compact in the full derived category has the consequence that you can compute the local cohomology functors as so. This is the same for this one. Okay, so this is what I think constants are called smashing localization. So we have this very handy formula for computing the local cohomology functors and the localization functors with respect to. Okay. Another consequence that comes from this property is that is the following. Yeah. Any questions so far? Yes. No. Exercise, find an example. Yeah. So for example, you can identify the V-local objects also as a subcategory of DR, and the compact objects there will not be compact in the big category in general. That would be an example. So look at P local objects in the derived category. They form a localizing subcategory, but the compact objects there are not compact in the big category. For example, in that category, R localized at P is compact, but it's not compact in the big category in general. Okay. What was that again, Neil? About what are you confused about? Yes? Okay. Yeah. But this is not what I'm saying. I'm looking at, no, this one, I'm looking at primes that are except P. Oh, did I say something here? Oh, I'm just thinking of it as, oh, did I make a mistake here? Oh, yeah. Sorry, obviously, throwing away things not, thank you, Neil. Yeah. Obviously, yes. Thank you, Arima. Yeah. Okay, so where was I? Oh, yeah. Okay, so another consequence of this is the following. So let's look at this, the inclusion. So let's look at this inclusion of the V-torsion subcategory into the full derived category. As I said, this has a right adjoint, which is gamma. I should have written it there perhaps. Okay, getting some exercise. Another consequence of this property is that if you take a collection of modules and you look at the natural map from here to this is, so the local cohomology functor commutes with sums, arbitrary sums. And this is then true also for LV. So now back to, and this is again a consequence of this fact that it's compactly generated, the V-torsion objects. Okay, so now we're in this situation. So this functor preserves arbitrary sums, it preserves coproducts. So that means that it has a right adjoint. Let me call that rho. And let me set gamma L lambda V to be the composite. So this, I claim, as the notation suggests, is completion along V. And so what I mean by this is the following. So let's say V is a closed set VI. Then for any module, one has the usual completion, I-adic completion, which one typically denotes this. So this is the limit of this system, right? The standard completion. Of course, then you can look at the derived completion. If you look at then this EI of M, this is applying the I-adic completion functor to any projective resolution of M. This is a projective resolution. So this functor here is the derived completion along I in the sense of Greenlees-May, left derived of the completion functor. And just by the fact that you have this adjoint pair, we get a map from M to this. Okay. So it follows from this. This is a functor that preserves coproducts, an exact functor preserving coproducts. So Brown representability tells you that you have a right adjoint. Such things, and that is what I'm calling rho. And I want to define this to be. So what this picture is telling me is that the inclusion is left adjoint to this. This is left adjoint to that. This one is the local cohomology functor. This is rho, some other functor. No, rho itself doesn't. This has an adjoint on both sides. Yeah. These are exact functors. Yes. It's a exact functors between triangulated categories. Right. No, so that's why it's a derived completion functor. It's the left derived of the completion functor. Okay, so this is okay. So what I want to discuss this a little bit. So so as I said already, when you're looking at the closed set, this is the I-adic completion. Now, if you look at let me see what I want to say next. Any questions so far? So the completions enters into the picture now. And for the rest of the talk, it's basically about the interplay between completions and local cohomology and what it has to do with stratification to some extent. Okay. Now, so let me say a few things about this completion functor. So let's look at the case when V is VI. Okay, and if you look at something in the bounded derived category, then the completion functor can be written like so. So the I-adic completion of M, or with respect to VI, this is the I-adic completion of the ring tensor with M. And it turns out that the left derived of this is the usual completion of R. And we're in the Noetherian case, remember, so the completion is flat. So I can even drop the derived and you get this. So if you're working in the bounded derived category, then the derived completion is just the usual completion of M. So this is, okay. But this is certainly not the case for general M. Not so for general M. So it's not smashing. So I think already in Constance's lectures, you saw in the stable homotopy context, some localization functors which are smashing and some that are not, and this is distinctly not. Oh, I should have said one thing. This functor here can also be realized as a homology localization. And I'll invite the topologists in the audience to see what it is. What is the homology functor that gives you this? Okay, so I was going to give you an example where this doesn't work. And the example is the following. So let's say you take a local ring R, Noetherian local ring, with maximal ideal M and residue field K. So if you look at the injective hull of K, and then you take the derived completion with respect to M. Any guesses as to what this is? Well, if you haven't worked with it, it's not a fair exercise. But let me tell you what it is and leave it maybe as an exercise. This turns out to be the dualizing complex for the completion of R. So you attended Aryaman's lectures. You know what a dualizing complex is, and it also came up yesterday in Suresh's lectures in the geometric context. This is the or R hat, the M-adic completion of R. So this is at once an indication that this formula doesn't hold and indicates why derived completions are so interesting. Because here's a beautiful description of the dualizing complex with sort of intrinsic, so to speak, but for the completion, of course. Right? So I leave this as an exercise. Okay, and okay. So working with completions, at least for me, is rather difficult. So there are some helpful tools to do this. Let me sort of recall two of them. So I was trying to number them, but I lost. Here are a couple of useful results. So one is Greenlees-May duality. So Greenlees-May equivalent adjointness or duality. Since I don't know how to finish it, I'll just leave it as Greenlees-May. So what they proved is that local cohomology is right adjoint to, so for all M and N in the derived category, local cohomology is left adjoint to derived completions. Oops, and so this is an extremely useful formula. So for example, and again, maybe I leave it as an exercise. Example exercise. So take any domain, okay, Noetherian domain, and assume that it is complete with respect to some non-zero ideal. R is iadically complete. So what this just means is that R is lambda R for some. Any question, Samik? Oh. Complete for some where? Yeah. Exactly. Yeah. Of course, I'm not giving it in. I didn't justify it. I just decided to introduce completions. So one can do it directly, then one has to show that it's adjoint. Okay, so what was I saying? Oh, you take a domain and something like this. And my claim is that if you look at the field of fractions of R, if you look at this, then this is 0. So this follows more or less directly from Greenlees-May. So it tells you in particular, okay. So here's a special case of, so for example, in particular, if you look at a power series ring in say a certain number of variables, so QR is 0, But again, Q is the field of fractions. Take a power series ring in any number of ways. Because R is amadically complete, where it's complete with respect to its maximal ideal. And this is the field of fractions of R. Yeah? So this is 0. So contrast this with the fact that, and this is something that came up, I mentioned already maybe in my second lecture, that if you look at X, so if you look at the integers and look at its field of fractions, this one is non-zero. The other exercise is to try and prove this directly without using Greenleaf's main. I don't know how to do it, or at least haven't tried. Okay. Oh, this is the field of fractions of fraction field of R. Field of fractions of R. So really, I'm computing these X groups. It's saying that there are no extensions of Q and R by R. Okay, so this is one very handy tool for working with completions. The other thing that I should mention, because it came up earlier, is that work of Dwyer-Greenlees. So I only told you half the story last time. So let me tell you the other part. So this is a Dwyer-Greenlees theory. So remember, what we had was a perfect complex. So it's a finite free complex, say, and E is the derived endomorphisms of E. And if you look at, we have the derived category, and we have these functors R. It went the other way. I talked about this functor. And we talked about this pair of adjoint functors, and I think I explained that this is gives you an equivalence between the V torsion part of dr, where V is the support of P, which in this case is the same as the support of the homology of P, which is a closed subset. So in fact, if I should have maybe turned the tables around, start with any V. You can always take a perfect complex supported on V, for example, the Koszul complex. So that gives you an identification of the derived category of V torsion objects with the full derived category of the endomorphism DGA, right? So this is one side of the story. The other side is that this is, I could have put it down here. The completions are right adjoint to this. So you have, so this itself has a right adjoint. And that is the functor. Let me call it P hash blank, where P hash is the R dual of P. So we have an adjoint pair like this, and Dwyer-Greenlees proved that this gives you an equivalence between this derived category and the category consisting of the V complete objects. So this is just looking at complexes M such that the natural map from here to this is an equivalent. So it's the things that are complete with this along V. You get an equivalence like so. So if you combine these two, you see that there's an equivalence between the torsion objects and the complete objects, right? This is, both these are equivalent to this one in the middle. So maybe I should finish the thought here. So what this says is that there's an equivalence between the torsion part of the derived category and the complete part of the derived category. And in fact, the functors are the L and R gamma. The functors that give you this equivalence are just the completion and the local cohomology functors. Here? Yeah, so this is P hash. So P hash just means the dual with, with respect to the ring. Thank you. here, this is the same functor as this one, R hom P blank. It's just the same functor, except that now it has a, right. Indeed. Okay, so to finish this thought, embedded here are identities like so. So if you look at the local cohomology functor, and you apply the completion functor, then this gives you an equivalence between these. And then there's also the pair where you can switch. So if you first apply the completion and then the local cohomology, all that remains is the local cohomology. So all these are very useful things to complete the work with completions and local cohomology. Not quite. No, it's on sort of the other side. It's a localization away from, so it's a localization with respect to some homology theory. It's the other side of the picture in some sense. Okay, so to get a better handle of these completions, let me introduce some invariants that are defined in terms of these things. Any other questions? Okay. Oh, the only assumption is a finite free. So the Dwyer green, you can get away with a little less on this side. Yeah, perfect, say, finite free. But as I said, maybe the right way to think about it is that you're interested in completion along some closed subset, and then you can realize it in terms of those functors by choosing a perfect complex with that as the support. For example, the Kozel complex. But not necessarily that's not necessarily the only choice. Okay. So the next thing I want to talk about is support and co-support. Okay. So if you look at a fixer prime O in spec R, and then as before, let this be the residue field of R localized at P. So you look at R localized at P, or the same as the field of fractions of R mod P. Yeah. No, what? No. Take this map, right? It's not an isomorphism unless here, the claim is this one. So the claim is that this induces an equivalence when you apply L lambda to this map. Oh, equivalence. Equivalence of categories. That's all, yeah. Okay, so last time already I talked about the support of an object. So if you take any M of VR, so then the support of an object is looking at the primes where M tensor this is non-zero. Tensor the residue field at P is non-zero, right? And in the same way, you can one defines the co-support. Actually, this comes up first in his book, Axiomatic Stable Homotopy Theory by Neal and company. So the co-support is looking at primes where there are no maps from a P to M. So this looks like it's a funny thing to do, but it turns out to be exactly the right thing to do. So this is the support of M and this is the co-support of M. Let me just say that although here I've exploited the residue field, so this looks like it's something special to the category of derived category of a commutative ring. You can interpret this also in terms of the functor. So you can, if you look at, so let me write, say, gamma P. This thing came up in Henning-Stock. The functor gamma P of, let's say, M If we take first localize M at P, actually the order doesn't matter. So this is the definition. So look at this functor, M going to this. This is the, you might think of this as the part of P supported, part of M supported exactly at P. So the P local, P torsion part of P. Then the support is also can also be described in terms of this functor. And that's at M tensor or gamma PM. So at this point, you see there are no tensor products. And this construction you can do very generally. So although I've chosen to introduce support and co-support using the residue field, you don't need residue fields to do this. And there's a similar thing for the co-support. You can look at sort of the P local, P co-local, P completion, which is completing R. This should be R. It's completing with respect to Vp of the functor M. Let me not worry too much about this. The only point I want to make is that there's a way to define support and co-support very generally. It's not something specific to the local algebra context. Okay. That's an excellent question. Yes, let me say something. Yes, Henning. No. These two functors are adjoint. Yeah, okay, yeah. Right. I thought you meant that these two. So I was talking about these two. So yeah, as Henning says, these two are adjoint. But at least this is, in my mind, a more manageable, at least to me, more comprehensible than this one. And let me talk a little bit about this. So for instance, if you take, so maybe it's an example exercise. Any example is an exercise because I'm not giving any details anyway. So if you take something in the bounded derived category, take something in the bounded derived category, then the support of M is the same as the support of the homology modules of the homology of M. And that's the same, therefore, so you're really looking at primes where the homology is non-zero. So it's the annihilator of the homology module. So in particular, this is a closed subset of spec R. Subset. Okay, so if you take a finitely generated object in something in dB mod R, the support is closed. So it's far from true for co-support. So co-support, it's not so easy to compute. In fact, it need not even be closed. So need not even be closed. Even, I'm talking about M in dB mod R. And so I don't want to get into this example, but let me just say this. So if you look at the power series in one variable and adjoin a polynomial ring to it, then this is an example of a ring for which the co-support of the ring itself. So it's not that you're working with some random complicated complex. This itself is not closed. So this example is due to Hedda Thompson, who has written Thompson with a P. So if somebody knows what the joke is about. Thank you, Suresh. It's a Tintin reference. Okay, so co-support is, in this case, is not closed. It is specialization closed in this example, but I don't know that this is a general statement. So the co-support can be quite complicated. It also can be quite small. So here's an example that's not so hard. So it's really connected with a computation we did earlier, or I hinted at earlier. Let's say when R is iadically complete, the co-support of any object of M. Yes. Yeah, so I don't want to say it because the thing is, yeah, actually, yeah, I don't remember the details. The thing is, what happens, okay, let me finish this. Okay, what happens is this is a ring in which, so this is clearly a two-dimensional ring, right? But it has infinitely many height 1 prime ideals. So maximal ideals. That's the funny thing about this ring. And it turns out all those are in the co-support, but some of them are not. So that tells you that it cannot be a closed subset. So it's some strange thing about the spectrum of this ring. It has many height 1 maximal ideals, although it's a two-dimensional ring. So, okay. So what happens is if I is iadically complete, then the co-support is in this for any M in dB mod R. So this tells you in particular, okay, so maybe it's worth pointing to making this even more, given an even more precise example. So here's another example. This is joke about giving an example to making your confusion more precise. Here's one. So if you look at this, and let's say R is arithmetically complete. Then the co-support of any module or finitely generated have I been putting 2s? No. Is contained in M for all M in dB. Whereas, of course, the support can be any closed subset of spec R, right? The support of something finitely generated can be any subset of spec R, but the co-support is always just the maximal ideal or nothing. Maybe in this, you should also, it's connected with what I said earlier. If you look at the co-support of the completion, co-support of the injective hull, it's not so hard to see that this is the entire spectrum of the ring. That's because this is a faithful injective. So given any module, there will be a non-zero map from that module to E. So it must mean that there are maps also from any residue field to E. So that's why there's a spec. Whereas this, of course, just to contrast, the support of this is just the maximal ideal. Okay, these are just by way of trying to convey that co-support is sort of a complicated thing. But I also want to try and convince you as we go along that it's a very useful thing, which is why one cares about it. Okay, so I said all this about co-support being difficult to compute. So maybe let me mention one result that is sometimes useful in computing a co-support. So the result is the following: for any M in D of R, if you look at the co-support and the support, of M. So already from these examples, you can see that they can vary, they can be quite different in general, right? So here the co-support is rather big, the support is small, whereas here the co-support is small, whereas the support can be anything. But one thing that is always the case is that they have the same maximal elements. So this is true. So it's a subset of spec. So it will have some maximal elements. It's sort of interesting that the maximal elements are the same. Okay, and it in particular, if you look at if one of them is empty, if and only if the other one is empty. And this happens, so for supports, we know this happens only if M is 0. So the co-support also detects non-zero objects. So this is called the co-support detection theorem. So this is sort of an important thing. Co-support of any non-zero object has to be non-empty. Right? Any questions so far? So let me move on. So this is, okay, so up to this point, everything that I've said is very general. You can prove these sort of results in great generality in sort of some TT category or. Yes, now I can say it. No. As long as M is non-zero, yeah. As long as M is non-zero, it will be equal to M, yeah, because of this result. Okay. So as I said, so far everything that I've said applies very generally. You can, for the stable module category of a finite group, or in general, any TT compactly generated TT category where you can set up this machinery, or in this stable homotopy categories, which is discussed in Neil's book. Now, the last part of today's talk, it will be about results that are specific to local algebra. In fact, it will be one result. Correct, homology is 0. Yeah. I should have said, I meant M is 0 in the derived category. Yes, yeah. So, exactly. Okay, so the last part is about finally. If you take any M and N in the derived category, it turns out that the support of the tensor product is the intersection of the supports. And the support of the function object, so the co-support of the function object, is support. So we have these two formulas here for computing the support of a tensor product and the co-support of So this one in particular tells you that this one implies that if you look at the Homs in the derived category between M and N, this is 0 or non-zero if and only if, I'm just writing down the obvious thing. This coupled with co-support detection is empty. I bring this up because so many of the concepts we have been discussing about cellularization and so on, and homology localization, they involve knowing when there is a non-zero map or when there are no maps between two objects. And this is why this formula is so important and interesting. It gives you a way to detect when there are non-zero map between two things. Okay. And in fact, the proof is not difficult in the context of commutative rings because there are residue fields. So let me just do one computation. I left everything as exercises, but this I can do. So let me pick this. So let's say take a prime spec out. So I want to know if it is in the co-support. So one must look at maps from residue field to this. Okay, then adjunction tells you that this is the same as maps from N. Now, here's another place where I'm using the commutativity. Because the ring is commutative, the R action, I can also take it. So this one is just equivalent to copies of the residue field, and the R action factors through Kp. So this would be the same as this. And this. So now everything is happening over this residue field. And so there are non-zero maps. So this one is non-zero. This object is non-zero precisely when Kp tensor M is non-zero. And this is non-zero. So what you've deduced from this is that P is in the co-support of the function object if and only if it's in the intersection of the support of M and the co-support of M. So it's fairly straightforward, but what was important is that Kp was a field. So we have these residue field objects that you can compute. First of all, that you can compute support and co-support using these residue fields, and we have them. Okay. The thing is, these two results together, this is basically at the heart of what are called these stratification and co-stratification theorems for triangulated categories. So these are classification theorems for, what was that again? Yeah. This is because, okay, so one way to say it is that in the derived category, the action of R on this factors through the residue field. That's what it is. So, if we were in the non-commutative context, the action of R on this would be through M, and I wouldn't be allowed to move it to this one. But because R is commutative, you can take the R action on either side. And that means I can take it through the residue field. So this is equivalent to some complex over the residue field, and R acts on it through the residue field, which is then gives you this adjunction. Or another way to say it maybe is that is equivalent to its homology. It's formal. Is it? Yeah. Oh, yeah, it's d-adically complete, yes. Right. Let's discuss this later. You're solving this exercise. Yeah. Yes. Close, yeah. So it should have, it will contain, see, okay, here's the deal. It's not closed, it contains all the maximal ideals. Yeah, that's because, yes, so it cannot be, yeah, okay. It contains all the maximal ideals because the maximal points in the co-support coincide with the maximal points in the support, which is spec. So it contains all the maximal ideals, but you're right, it doesn't contain T. It's contained in VT, so it must be that. Good. Was that clear? If you've put together the exercise I said already about, if you put together this fact this tells you that the co-support of this contains all the maximal ideals. On the other hand, it must be contained in V of t because it is p-adically complete. And it can't be a closed set. If it was a closed set, then it wouldn't contain all the maximal. Okay. No, it doesn't. It doesn't use that observation, no. Yeah, it doesn't seem to use that observation, not this way. Does it, Snake? No. Okay. Oh, by the way, I did forget to mention one thing. I should have said it. One fact that comes to mind. Let me finish this. Okay, since we're discussing this point, let me just record it here. So I did say that co-support is difficult to compute. So there's a guy called Nakamura who proved the following very nice result. That if you take an affine algebra, so take a polynomial ring, I think he also allows polynomial rings over discrete valuation or over the integers. But okay, let's say K is a field and you look at an affine algebra, so a finitely generated K algebra, then this co-support and support coincide for all n in dB. So this is sort of this is an interesting result. But there are very few computations about co-support. This one is sort of one comprehensive one. Take any polynomial ring, factor out any ideal, so affine algebra. Take anything in the bounded derived category of such a thing, then the co-support of the object is the same as the support, and in particular, it's closed. Okay. So what was I saying? Right. I said these things are pertinent to this stratification theorems because it's not so hard to go, this one. This result, this formula for the co-support immediately gives you the following theorem that, well, at this point I'm running around in circles, but there is a straight path to this theorem going through that. Namely, there is a bijection between localizing subcategories of dr and arbitrary subsets where these functors came up before, right? Maybe in Henning's lecture already, and also in Natalia's. So what do we do? We should let me state in this direction. If you send a localizing subcategory, say S, to the union of the support of objects in S. And you can guess what the inverse is. And this restricts to give you an equivalence between a bijection between, so this is a bijection. And this restricts to give you a bijection between the thick ideals, thick subcategories. Everything is an ideal of the perfect complexes. And specialization closed subsets of spec. Okay, so this is roughly what it means for the derived category to be stratified by the ring R. And there's also an analogous result. Maybe it's not worth writing it out, and where instead of localizing, you look at what are called co-localizing. Co-localizing subcategories, namely, these are triangulated subcategories of DR, which are closed under arbitrary products. And where you look at not sub, but co-sub Of course, this is the same. So that's called co-stratification. The derived category is also co-stratified by the action of the Iyengar. So in fact, it turns out that co-stratification is somehow the more basic thing that immediately implies stratification, although in some context, Natalia and her friends have managed to prove that you can also go the other way under certain conditions. Okay. So finally, I've discharged my duty and mentioned stratification and co-stratification. I'll stop here. I know I'm ahead of time, but it doesn't matter. Somebody was saying this is going to be a long day. This is my contribution to that.
Are there questions? So co-localizing you have defined.
Oh, I didn't define it formally, but just that they are triangulated subcategories closed under products.
Products.
Yeah.
And the compact version below?
It's the same, right?
It's the same thing.
Yeah. Oh, what? Oh, so as I said, co-support first appears in axiomatic stable homotopy theory by Harvey, Palmieri, and Strickland. But then Dave Benson, Henning, and I had wrote a paper about this in the context. Well, in general, our main goal was to understand, and we proved this analogous result. Henning already mentioned that we proved this in the case of a stable module category of a finite group or group scheme. So there's also the co-localizing versions. The local version for co-localizing subcategories also exists, and it comes in two papers. So we did it first for groups. It's called co-localization. I think, is it correct? Co-localization and co-support, something like that. And then we have a paper from this. So maybe that's the basic. I mean, Neil's book and that paper would be the basic reference for all this machinery. And there you will find all the results except, well, including this one, but there you'll see that much of this really is can be done for general triangulated categories, except these two. These are crucial. These are somehow, if you have detection and this, then you really are in good shape. Detection, if you know that support and co-support detect non-zero objects, and you have these formulas, then it gives you a lot of information about the classification of, well, it really gives you the classification of localizing and co-localizing subcategories. So much of the hard work in the finite group case is proving these formulas, because everything else is there for free almost. Free meaning it's true in very great generality, but proving these formulas in the context of finite groups takes much more work. In the ring case, it was fairly trivial, right? It's just this, but it's not so for finite groups or other contexts. Yeah. Oh, okay. Yes, happily. Sure. You want me to solve my own exercises? So the thing about the injective hull is that you have a local ring, so a Noetherian local ring, right? And we looked at the injective hull, and a claim is that for any M in dr, R hom and E is non-zero. So it's a faithful co-generator is what I'm saying, injective. So this is and really one is interested in this. It's basically a statement about homology, right? Maybe I should not, okay. Is non-zero, correct? So this statement is basically saying that the homology is non-zero. But since this is an injective, this is equivalent to the statement that you can forget about the derived business. It's just a statement that there are maps from the homology to E, because E is injective. Now, because it's basically one of the so what it says is you can assume that M is a module. So enough to prove when M is a module. If you have a non-zero module, you want to prove that there's a non-zero map to the injective hull, right? Now, I now reduce it even to this finitely generated case. So pick a finitely generated submodule. For example, you can even pick a cyclic module. So assuming, so pick X in M non-zero and look at this as a submodule. So let me write check for this, this is really, it's matrix duality after all. So it's just saying that matrix duality is a faithful functor. So this gives you a map from here onto this. So it's enough to prove that this is non-zero, correct? But now you reduced it to the cyclic case. So may assume M is R mod I. And now you can construct a map from here to K, because you can, after all, you can map it to R mod M, and that embeds in K in the injective hull. So that gives you a non-zero map from here to E, and that does it. Suresh, you saying something? Oh. So yeah, so this is why, in particular, if you stick in any residue field, you'll always have a non-zero map, which is why the co-support is everything. In fact, the co-support, being non-zero is. So the co-support being non-empty tells you that there must be a non-zero map from anything to that object. Sorry, if the co-support is the full spectrum, it comes from here. If the co-support of N is the whole thing, this is spec R. As long as M is non-zero, this formula tells you there must be a non-zero map from M to that object. That was a special case.
So one question. This last statement, is it true for a scheme case?
Yeah. Oh, you have to be, this is true, yes, yeah.
Even the last detection of
hang on.
morphism.
So what do I have? We have to be now careful about TT, because in the scheme case, you have to be careful about TT, tensor product. What is true is that, I see, yeah. No, so one has to be careful. I think this is true that the function object is non-zero if and only if this, but this being non-zero, if this intersection is non-zero, it means that M tensor something perfect. There's a map from M tensor something perfect to N. It doesn't mean that there's a map from M to N itself. That's what it is. Because the unit of the tensor product does not generate the category. That's the problem. Because this is only looking at maps from the unit. One direction will be okay, but not the other.
Are there other questions? Okay, then let us thank the speaker once again.